and phi becomes phi c. When theta 1 is equal to theta a, it means this angle phi will be greater than the critical angle or equal to critical angle. So phi is equal to phi c. So now you can write this sin phi is equal to n2 upon n1. When theta 1 is equal to theta a and phi is equal to phi c, then one can write sin phi is equal to n2 upon n1. Right, so I have to put this value in the equation number 2. So equation number 2 is what? N naught sin theta 1 is equal to n1 square root 1 minus sin phi sin square phi 1. And what I did here, what I basically mentioned here, so I have mentioned the limiting case. Limiting case is what? Limiting case is this one. This light ray get reflected into the core only when this phi 1 which I have mentioned here is equal to the critical angle or greater than the critical angle. So then that time this theta 1 will be the acceptance angle. So theta 1 is acceptance angle theta A and phi is equal to phi c. Then according to the Snell's law, as we have already derived it, sin phi will be equal to n2 upon n1. So now I am putting this value here. So result becomes n naught sin theta 1 is equal to n1 square root 1 minus n2 square upon n1 square. That is n1 square minus n2 square upon n1 square. When n1 square comes out from this root, that cancel out this one. So you have only this n1 square minus n2 square square root. So n naught sin theta A is equal to square root n1 square minus n2 square. So from this mathematical derivation we have obtained this result, that is n naught sin theta A is equal to square root n1 square minus n2 square. So now one more form of the numerical aperture, that is in terms of the fractional refractive index. That fractional refractive index is defined by n1 minus n2 upon n1 ratio. So this delta is known as fractional refractive index. Fractional refractive index delta, and that is the ratio of these two, n1 minus n2 upon n1. So by using this square of n1 minus n2 square, we can find out this result. So n1 square minus n2 square can be written as n1 plus n2 divided by 2 into n1 minus n2 divided by n1. So what I did here, I just break up this difference of these squares and multiply by 2n and divided by 2n1. So now further we know that n1 is almost equal to n2. So the average of this term one can write as n1, and this is n1 minus n2 upon n1 as it is, because it represented to the fractional refractive index n1 minus n2 upon n1, and this is 2n1. So 2n1 into n1, it becomes 2n1 square. So this is n1 square minus n2 square. So now I am putting this value into the formula, and that is square root of n1 square minus n2 square is equal to, the value of it will be 2n1 square, and this is n1 minus n2 upon n1 is delta. So the result will be n1 square root 2 delta. So now we have three relations in this particular topic. Number one is n naught sin theta a, that is equal to the square root of n1 square minus n2 square, and this is again equal to the latest result which we have find out right now, n1 square root 2 delta, where delta is defined in terms of the ratio. Delta is n1 minus n2 upon n1. So by this way, mathematically one can define the numerical aperture. So numerical aperture is defined by the n naught sin theta a square root of the differences n1 square minus n2 square, and again the third formula is n1 square root 2 delta, where delta is the fractional refractive index. So the numerical aperture is often used with the fiber in air, where n naught is unity, refractive index of the air is 1. So it is simply equal to n naught equal to sin theta. But one more important point is here. Suppose this optical fiber is kept into the water instead of the air, then the refractive index of the water will be considered here. Right now I have used n naught for the air, but if suppose this optical fiber is kept into the water, then that time we have to use the refractive index of the water. So then formula will be for the numerical aperture nw sin theta e. So instead of nw, then one have to write nw. nw is the refractive index of the water. So now, as I defined here, that numerical aperture is often used to with the fiber in air, where no n naught, that is the refractive index of the air, is 1. So it is simply equal to sin theta e. Right? So it may also be noted it may also be noted that the incident this extreme ray basically sometimes is called as meridional ray also. This is the extreme ray which makes maximum angle theta A, right? So this extreme ray which enter with the maximum angle is known as what? Extreme ray and meridional ray. Meridional ray, right? So it has been maybe also be noted that the incident meridional ray over the range range is basically what? This is the axial ray. If a ray passes through the axis of the core, that is known as axial ray, AXIL ray. So there are two types of ray in this geometry. One is the axial ray and second is the extreme ray or meridional ray. So the limiting value of the theta 1 is 0 to theta A. This is the maximum angle and that is theta A. So from extreme ray to meridional ray, the angle is theta A and that is the maximum angle. So range of theta 1 in this case will be 0 to theta A. So it may also be noted that the incident meridional ray over the range 0 to theta A will be propagated within the fiber, So this is the condition that which ray basically travel into the optical fiber. For that, if a ray satisfy this condition, this particular condition, if the theta 1, that is the incident angle, lies between 0 to acceptance angle. So if a light ray, this is the light ray basically which enter through this range, so it is 100% sure that it will get reflected into the core and it will follow the multiple reflections. So the important point is this one for the incident light ray. So these are some basics about the numerical aperture, and we have discussed it about in terms of the fractional refractive index and the core cladding indices, refractive indices. So numerical aperture basically MA is equal to N naught sin theta A is equal to square root N1 square minus N2 square is equal to N1 square root 2 delta, where delta is the fractional refractive index. So this relationship between the acceptance angle, refractive index of the air, core and cladding is important. So the above relationship for the numerical aperture are very important and useful. Measure of the light, useful measure of light collecting ability, light collecting ability of a fiber. So generally the numerical aperture we define in terms of the light collecting ability of an optical fiber. So light gathering ability of an optical fiber. So here in this formula, if you see it carefully, so numerical aperture basically this relationship n naught sin theta a square root n1 square minus n2 square is equal to n1 and square root 2 delta. This is independent from the core diameter and the wavelength of light which we have used. Right, so numerical aperture is independent from the diameter of the core. Okay, it was the basics about the optical fiber. In this particular lecture, I have covered the basic concept of optical fiber. They were total internal reflection, acceptance angle, and the right now numerical aperture. So these three things I have discussed into this particular lecture. If you have any question about these or any problem at any point, you can message me below this site.